In this recording, we're going to look at the fact that kernels and images of group homomorphisms are subgroups of the domain and codomain, respectively. So throughout this tape, we're going to be looking at the situation where G and H are groups, and F takes G into H is a group homomorphism. And the kernel is nothing more than everybody inside the domain, such that F sends that person to the identity over in the target group H. And the image of a group homomorphism is everybody inside the target set, such that there exists someone inside the domain with F of that someone being equal to little h. Now, the claim that I want to be looking at today is made in this theorem. It says that if we do indeed have a group homomorphism, then the kernel is going to be a subgroup of the domain, and the image is going to be a subgroup of the codomain. Well, the proof of this theorem is to basically prove each of the subgroup relationships independently. So we're going to start with trying to prove that the kernel is a subgroup of G. And we're going to use the subgroup criterion. So what that means is we're going to let two elements be inside the kernel of F. And I simply want to remind myself that if we can show that the inverse of the first one times the second one belongs to the set kernel of F, then we know that the kernel is indeed going to be a subgroup by the subgroup criterion theorem. And so what I want to do is I want to think about, what does this particular hypothesis buy me? Well, it turns out that it buys me quite a bit. A is inside the kernel of F says F of A is equal to EH. And B inside the kernel of F says F of B is equal to e to the h. Now, the fact that H is a homomorphism also lets me say something else. This particular equation right here lets me also say that F of A inverse is going to be EH inverse, which is just EH. And that's from one of the previous videos. So now we're actually ready to look at this. I'm going to think about feeding A inverse B to F. In other words, I want to actually look at what is F of A inverse times B. Now, F is a group homomorphism, so this is F of A inverse times F of B, since F is a group homomorphism. But we've just gotten done figuring out that F of A inverse is nothing more than EH. And we also know that F of B is equal to EH. So F of A inverse times B is now EH times EH, which is just EH. In other words, what we've got is that A inverse B is sent to EH, and hence it has to be part of the kernel of F by the definition of kernel. And that means that the kernel of F is indeed a subgroup of G by the subgroup criterion. Okay, well, once we have that, we now turn our attention to, what about the image? So I'm going to think about that. I'm going to let two things be inside the image of F, and I'm just going to call them H1 and H2. Again, our goal is to show something about H1 inverse times H2. If we can show this funny little product, H1 inverse times H2, if that belongs to our chosen set, the image of F, then we can conclude that the image of F is indeed going to be a full-fledged subgroup of the target set H. Now, what again I want to do is I want to think about what does this hypothesis that H1 and H2 are inside the image of F, what does that buy me? And again, it turns out that that hypothesis is going to buy me quite a bit. H1 inside the image of F is going to say there exists some G1 inside G such that F of G1 is equal to H1. And H2 inside image of F is going to say there exists a G2 inside capital G such that F of G2 is equal to H2. Now, because F is a homomorphism, we also know something else. We know that F of G1 inverse is equal to F of G1's inverse. And because F of G1 is equal to H1, we know that F of G1 inverse is now going to be H1 inverse. And this is all because F is a group homomorphism. So now look at this. I'm going to look at H1 inverse times H2. Now, what is H1 inverse? H1 inverse, tracking it back, is equal to F of G1 inverse. So I can write that H1 inverse as F of G1 inverse. And H2 is just another name for F of G2. Now, F is a group homomorphism. So I can take this expression here and I can rewrite it as F of G1 inverse times G2, and this is because F is a group homomorphism. But now what I want to realize is I want to look at this particular element here. G1 inverse times G2 is in G. And I know that because G is a full-fledged group. And G1 and G2 both belong to G. So now what I have is that H1 inverse times H2 is F of some element in G. Well, what that says is that H1 inverse times H2 is indeed an element of the image of F by the definition of image, and hence we can conclude that the image of F is a subgroup of H by the subgroup criterion. And so at that point, we're now done.